Hello there, thank you for joining me again today. Welcome to the wonderful world of RF and electronics engineering. On the bench today for repair is a Rhode Schwarz spectrum analyzer. Quite a nice spectrum analyzer, quite a large beast at that in comparison to other spectrum analyzers that we've reviewed on this channel. This one boasts a frequency range from 20 Hz to 7 GHz. It's FSEB 30 model, and it's also manufactured by Rhode Schwarz. Now, this was brought to me by a radio amateur who's recently acquired it, and had noticed that the only issue with it is the RF level coming into the RF socket there, the input socket, that the level was reading incorrectly on the screen. So when you're looking at the signal trace, the amplitude is wrong. Now everything else, according to what he says, seems to work fine. It's just the amplitude that's the issue. So what we'll do, we'll connect it up, we'll have a look, verify that fault, and then we'll take it from there. We're quite lucky with this one because I've actually got the service manual for this test set, albeit electronic, downloaded on my computer. So that's going to help us a lot, because there's nothing worse than trying to tackle a fault like this without any service information. And that's quite difficult when it comes to Rhode Schwarz. So I'm quite lucky there that I managed to get the service manual. Anyway, we'll turn it on. We'll go through its own calibration routine and see what happens. And we'll also do some measurements to see whether or not this fault shows itself. So stand by and we'll connect it up. Right, we're ready to switch it on now. So that's what we'll do. We'll press the power button. Now we've got it connected up and everything to the mains. Fingers crossed to see what happens. Let's come up with this screen, analyzer BIOS, copyright Rhode Schwarz. It says booting. I can hear the ID hard drive heads moving about inside. Oh, SATA drive. It's not an SSD on this one. It's quite an old one. So it's chuntering away, loading its software up and everything. Possibly might flag up any errors at this stage, which will be interesting. So I'm just keeping an eye on the screen just to see what errors we get, because you never know, it might come up with an error. So I'll just keep an eye on it. Transputer download successful, so that's good. Download of a binary file for synthesizer. So that's what it seems to be doing, downloading some files from its hard drive. They all seem successful so far. Anyway, download of another binary for detector. Gate array found, it says. No errors yet. So, seems to be chuntering away the hard disk, loading up various files. What if it's like a DOS-based system or a basic? And all these are successful, all these DLF files. They are all okay, no errors there. That's good. Now we're at the screen here. Okay, so didn't seem to boot up with any errors, which is a positive sign. That's a good thing. So now we can have a look at the calibration feature on the test set. Now, on this we've got a cal button here, so we can go into a calibration screen and see whether we can calibrate the instrument, and see whether it fails that. So if we go into cal for a moment, and then we've got another option here which has come up on the other side of the screen, which is cal short, cal total, cal resolution bandwidth. I think that's cal logarithmic, and cal local oscillator supply, cal low sup. So we'll do a cal short, which is the top one, and I'm not sure if the screen's actually touch screen. No, it isn't. You have to press these buttons. Okay, so we'll do a cal short. Let's see what happens there. Now, just to explain, it's already found an error. Look, if we're zooming on that message, it says there, warning, calibration failed. Okay. Now, it hasn't told me what it's failed on. looking at various parts of the screen. There's no information there that says what's failed, so I might have to look deeper into the analytics on that. But basically, top and bottom of it, it looks like as if it's not got any further there. So what we got there, cal total. Shall we go for cal total? What does it do on cal total then? Doing something. It says warning, calibration failed on that as well. So interesting. Now we have got a little green marker next to the button there. Now I think it says that I'm not sure why that little green marker's there, but I might have to look in the manual for that, see what it says. Now just to explain a moment is that on this instrument, because I've just read a little bit of the manual, the service manual, unlike a lot of other spectrum analyzers that we repair on this channel and demonstrate, such as Hewlett Packard for example, you normally have another socket, BNC socket or TNC whatever, and it says cal output, and then you'd link that socket to the RF in socket, and that would then connect the calibration signal to the RF in. You'd then enter the cal sequence like we've just done there, and it would then obviously calibrate itself against the cal reference. Now on the Rhode Schwarz spectrum analyzer, it's more advanced than that, in that the RF input here internally switched via RF relays through the attenuator section to the calibrator module. So that is all internally done, so there's no external connection required, and that's the noises that you just heard when we went into the cal menu, when it went clunk click and it was trying to then switch in all the different paths in order to calibrate that signal. So it could be that, you know, there's an issue with the calibrator, etc. It's possible, but what we'll do now, because I can't see any errors that's come up on the screen, there's probably some in-depth level error chart in there somewhere that'll tell us what the error codes are and what they mean, so I'll need to look into that now further in order to find out what the issue was with the failed calibration level. That's assuming it's got that level of analytics on it. But what we'll do now, we'll just jump into it a little bit here. We'll connect a signal from our signal generator to the RF input port on the instrument, and then what we'll do, then we'll see whether the level going in actually measures the same on the screen. So that's what we'll do next, so bear with me. Okay, so we're inputting a signal now at 100 megahertz, and we're reading the RF level at minus 43 dBm. So that proves that the signal that we've got coming in is 43 dBs below what we're actually feeding in. I'm feeding in 0 dBm at 100 megahertz from the IFR signal generator that I'm using in this case. I'm using very low loss, obviously aerospace grade Anritsu cable, which links up to the signal generator. So what I'm going to do now, I'm going to widen the span out. Let's have a look here, span. I'm going to change that now to, I'll put it to 3 gigahertz. So we can see the 100 meg tone down here quite clearly. Now what I'm going to do is I'm going to put an increment on the test set. I'm going to go back to markers. We can do a search there, and that's again telling us what the level is on that particular tone. Bear in mind we've got a 3 gigahertz span now set up. Now the signal generator that I'm using for this first part of the test only goes up to about 2.51 gigahertz. So I'm going to set an increment on that of 200 megahertz, and each time we move the frequency I'm going to check to see if the levels are the same. Now if there's a fault within the instrument's RF path, for example, such as an open circuit strip line, or a broken RF component, or something that will cause an RF transform to occur. Obviously when we've got RF trying to jump a gap in a PCB trace or a defective component that's effectively going to open circuit, then you can get different performances, different frequencies. Obviously, the lower the frequency, the more loss there would be. As we would then increase the frequency, then the transform would occur where we can effectively transfer the RF signal across the air gap much easier, and therefore the signal level will go up. So I'll be expected to see a curve going up as the frequency increased. So that's one little test that we'll do anyway, and that'll sort of prove whether it's you know, a major fault, as in a broken RF trace or something like that. And it also, as well, if an amplifier or a filter is not performing correctly, that can also show that up, because at different frequencies, obviously the amplification may change in linearity depending on the type of fault that it is. So that's what we'll do now. I'm going to set up a 200 megahertz increment on the SIGGEN, which I'm doing now. So if I go to increment, I think it is on there somewhere. Let me just have a look at my SIGGEN and see what I can do. So this is the IFR that we're using, so I'm just going to set that up now, and I'll be back with you in a very short time. Okay, as carry on now from that first measurement, we're going to see what it's like right up to 2.5 gigahertz to see whether the level changes a lot. Now, bearing in mind, of course, it's reading about 38 dBs below the 0 dBm reference signal that we're currently putting in. So I'm going to go up to the next increment now, which is 300 megahertz, and we're going to increment it in 200 megahertz steps, as I said before, right up to the limit of this particular SIGGEN that I've got on, which is 2.5 gigahertz. So we'll see whether the level changes. So we're going up now to 300 megahertz, and let's see whether we can get that marker. It's still the same, minus 38 dBs. So again, 500 megahertz. Still the same. So the level's been pretty consistent so far. 700 megahertz. .38 dB, 39 still. 900 megahertz. Still the same. 1.1 gigahertz. Still the same, give or take a dB. Yeah, 1.3 gigahertz now. Now we're going up to 1.5 gigahertz. Still maintaining the same level as we were before at minus 38, 39 dBm. Now we're going up to 1.7 gigahertz. And again, the same level again. 1.9 gigahertz. Same level at minus 40, so it's 2 dBs difference between where we started. 2.1 gigahertz now. Minus 40 dBm. 2.3 gigahertz. So we'll see whether that works. Minus 40. It's fairly consistent. And now 2.5 gigahertz. So we've reached the limit of this particular signal generator. So that's basically more or less uniform, give or take 2 dBs, right the way from 100 megahertz to 2.5 gigahertz. And I think that sort of proves really that the actual frequency response is actually quite uniform in level. So whatever the fault is, it's obviously across the entire frequency range of the instrument, which is worrying, because it looks as if it could be something in the conversion stage or RF attenuator stages on the front end of the RF module, which may be causing further complications. So it does look to me like as if potentially we could have an issue. We could have an issue with the RF attenuator section somewhere in the RF modules, or something more serious than that, due to what we've found so far. But at least it proves that as it tracks across from basic 100 megs to 2.5 gigahertz, which is where we're at now, then yeah, it does look as if it's more serious than first thought. But we'll delve deeper. Right, before we go any further, what I want to do is just check the obvious with the instrument, rather than zoom into whipping the lids off and then you know, dissecting it and trying to fault find at this stage. I just want to look at the obvious first. I just want to retrace over what we've done so far, just to make sure that it's not operator error or a setting in the configuration that maybe is causing an incorrect measurement. I doubt that will be the case, because even if there was an option on the instrument, which I've yet to find, to set an external attenuation level, where you use an external attenuator in conjunction with the RF input, you can put the offset for that attenuator in the memory, and then while you're using that attenuator, the measurement will be offset. So in other words, you can use the attenuators externally from the instrument to measure higher levels of RF power than what the instrument can take if the RF's directly connected to it. And there's an offset setting in most spectrum analyzers which allows you to set an external level of attenuation. So that's a consideration, but with the experience that I have with test equipment repair, normally even if that was applied, it wouldn't affect the calibration, which is doing here, because obviously when we go to cal and we do a cal short, it's then failing on the calibration. You know, calibration failed. So if that was the case, then you know, we wouldn't be getting that message. We would, however, be getting a different level reading up there, but we wouldn't be failing the calibration. So that's the difference between an operator error, if you like, by setting an external level of attenuation, which isn't applied at the time when you're doing your measurements, thus causing an incorrect level reading to be shown, versus it failing calibration. So, you know, obviously if it's failing calibration, there's something more serious. So one of the other things that I wanted to do was to go into, I think it was setup here, and within setup then we've got various things, including, for example, options, service, general setup, that kind of thing. Now in general setup, I wanted to see whether there was an option for setting external level of attenuation, but I couldn't see that there. It's just date, time, communication ports, things like that. So that was it really, apart from under service we've got an option there where we can service the RF input, but when you select that, it's then wanting you to input a password, which is here, enter the password. Then it comes up with this. I don't know what the password is. If we ever get to that stage of having to do that, I may have to you know, try and guess it and see whether I can get round it. Then I couldn't see anything else. The transducer, that's totally different. Obviously I couldn't really see anything that stood out that said anything about an external level of attenuation. And likewise as well, under, I think it was the reference level, you can have you can set the reference RF attenuator manual, RF attenuator auto, and there's different types of attenuation that you can select, manual, auto, etc. But the RF attenuator on this instrument is set by this button here that says input. And now when we press the input button on the instrument, then what it does, it brings up the available options for the input attenuator. So at the moment it's set to auto normal, sorry. If I select manual, it's set to 10 dBs of attenuation. Now if I press the up and down buttons, obviously I can select 20, 30 dB, 40 dB, 50 dB, 60 dBs of attenuation and 70 dBs, and then that's the limit there. So it keep coming down again, 40, 30, 20. When I get to 10, I can't get 0. But what's interesting is if I press 0 now, followed by dB, then we get 0 dBs of attenuation. So we've gone through all the switchable steps within the RF attenuator on the input. So obviously we can hear the relays clicking, which I'm sure you can. But we just need to check that now, because I think when I was making the measurement earlier, it may have also been set to 10 dBs. And what's interesting as well, in the service manual, which I'm going to go into in a moment, it explains that if a calibration fails on the cal short setting, to set the attenuator to 0 dBs. But I do find it interesting though how using the cursor keys you can select 10, 20, 30, 40, 50, 60, 70 dBs of attenuation, but the cursor down bottoms out at 10 dBs of attenuation, and you can only reach 0 dBs of attenuation by selecting 0 on the numerical keypad and then pressing dB. So I find that quite strange. I don't know why they'd want that to be off limits to the cursor key, considering the increments are set at 10 dBs anyway, so don't understand that. Anyway, not to worry. What we'll do is we'll connect up our signal generator now. Now I've got my Marconi signal generator outputting a frequency of 1 gigahertz at 0 dBm level. So we've got 0 dBs of attenuation on there, so let's just see what happens when we connect this signal up. And let's just make another measurement now with 0 dBs in there. So we'll set center frequency 1 gigahertz, and we'll set the span to 1 megahertz, and we'll put the markers on. Normal marker, which has selected the peak at minus 36 dBs of attenuation, which is shown here just in the top. Now obviously that's quite a way off. The actual level that's coming in is 0 dBm, so it's quite interesting how it's such a long way off still, even at 1 gigahertz. But if I were to change the input now, the RF attenuation on the input, and then we can see what happens with the signal. So if I select the input there, and then where is it, input, manual, that's it, right. So though it's reducing the RF signal visibly, the level is still remaining constant. So that's showing us that the attenuator is definitely working, although we'll need to do some verification tests on that to prove it further. But yeah, it does just seem to be a level issue, obviously. But I can't seem to see if there was a setting for the RF input attenuation, external attenuation level. Now there is a between 50 and 75 ohm options available for the impedance of the input port, obviously, to take that into consideration. There's nothing else that I can see This config button here displays the hard drive files and things that are stored on hard disk, some of the settings that are there. There's nothing else that's sort of like a deep level system apart from just the setup key, followed by either service, which then gives us input RF controls, etc. Now there was a mixer level thing that I spotted earlier as well, but that wasn't under any, I think it was just under center. Where is it now? Oh, it might have been under reference. Mixer level just there. Select that. Now currently the mixer level is at minus 30 dBm. Now if I adjust that, you can minus 10 dBm limit reached, and then go further and it's minus 50, minus 55, 70 dBm, 80 dBm, 100 dBm. So basically that's not made any difference anyway, but I just thought I'd look at that anyway just to see what if that made any impact. You never know. I noticed the date and time on the instrument is wrong, so another consideration that I had was it the case that it's had a software reset, as in the RAM, with some of the calibration data has been lost, because perhaps the 3-volt battery for the RAM has leaked, or has, you know, packed in with age, so it may have lost all its service settings through that. So it may not be a component failure as such, it could also be a loss of calibration data due to memory loss, with the battery not backing up the memory. So there's that consideration as well. So really we're sort of clutching at the straws a bit, but just trying to rule out first of all operator error. It did say in the calibrate instruction, which we'll look at shortly, about the cal normal to set the dBm to 0 dB if it fails a cal. So that's 0 dB, which is there. Then it said go to the cal menu and select cal short and see whether that calibrates. But then it says calibration failed still. So again, I was sort of hoping, fingers crossed, that it would spring into life, but obviously not. There's more wrong with it than we think. I can't see anything else there. That's a configuration section. You just got mode. You have to clear that message first. You just got mode. You can have it as a analyzer, and that's the only mode it does. Under setup, you've got options. There's no options fitted. Then of course you've got versions, options, blah blah blah, reference external reference frequency, service, general setup, right hand key. Basically says that there'd be more options, but there isn't. That's for sort of status. Hard copy for the what's on the screen for printing. That's a configuration. The system, info, self-test. So let's go for a self-test. What I'll just disconnect the RF input signal first before doing a self-test. It's makes good sense to do that. That way then we're not going to ruin any signal. So self-test, execute tests. Let's see what it does now. And see what happens. See if it fails any of them. Right. RF converter. Right, self-test failed. So what it says for self-test failed is, if I can just have a look at that on the screen, RF modulator, RF converter. Okay. So it says it's self-test failed on RF modulator or module. I take it that word there, module, will be, because it doesn't have an E at the end of it, as in module. Does it mean modulation? I don't know, because I've seen that word used to express modulation, module, so without the E at the end. So maybe because it's German translation to English, that the way that they're pronouncing it in English is, it means module, RF converter, RF module, RF converter, or does it mean RF modulation and RF converter? I think it would be helpful if it had put the E at the end of the L, so that it would express what's actually wrong, as in a module, or is it modulation, module? So again, when you come across technical terms in a lot of service manuals and test instrument error codes, module with an L at the end is often short for modulation. So I think this is a different meaning though. It means RF module without the E at the end. Anyway, not to worry. So I think the next thing to do then is to have a look at the internals. I think I'll start with the power supply first to check the power supply voltages before we do anything else with the RF side. I think that'll be most prudent to do that, so that we can prove that the supply levels are correct. Obviously, if the supply levels are not correct, then there's no point in hacking away at the RF sections, the RF attenuator, the RF up converter, down converter, the mixer modules, things like that, and going into deep level with that. Only later on, much further down the road, find out that the power supply is at fault. So I think it'll be a good point to start there. Okay, so what I've done on the system menu here, I've gone into info, and down here we've got system messages, self-test, the firmware versions, hardware options, etc. So if I go into system messages, so this is what we've got. Now, interestingly enough, let's have a look here. Let's see if we can just read that a bit. Missing reference. So that's interesting. Now, it seems a bit odd that. 4th of August, that's today's date, and then obviously the calibrate, the error numbers 10050 is the same for all of them, and then it's this number here, so they may mean something in the service manual. But yeah, so anyway, it'd be interesting to see what under info again. Clear all messages. Well, I'm not going to do that. Clear message. I'll just preset the instrument. Oh, hang on. You've got to click clear to get rid of that. Right. Info. Right. Self-test. What does it do under self-test? Execute test. So I'll just remove the RF signal on the input to the connector at the front. Just get rid of that for a moment, and then we'll let it crack on with its self-test and see what it does. It's obviously on with something. Self-test failed. RF module, RF converter. Right. I'll clear that one then. So that's that then. Now, well, it's not allowing me to clear it now, which I'm a bit. How the hell do you get out of it then? Oh, there we go. Right, so I think it's time to look in the manual and see what the good book says. Okay, so we've got the bottom off the unit now. This is where all the fun happens, obviously. So it's a very similar architecture internally to the CMS series of radio test sets. You'll see on my other videos that I've done on the CMS33, the CMS54 radio communication test sets. They have the very same architecture internally as to the spectrum analyzer, where they have modules which plug into a motherboard, which is this board here in the middle with multi-way sockets, and each module plugs in to that frame, if you like, and then you have the interconnects between them on the RF lines, which then enables various functions and options. So I can see there's a card missing down the middle here and one here, so I presume they'd be for the track gen option if that was fitted on this model. This option hasn't been fitted on this particular spectrum analyzer. It's got a blanking plug where the track gen output would be, so I assume that's what those two module slots are for. It makes it a little bit more difficult to service this instrument, because if we do get a defective module that needs to be unplugged, raised out the test set, and then obviously the cover taking off, to gain access then with trimming tools to adjusting potentiometers, RF caps, or to do any onboard measurements using test equipment, it makes it extremely difficult to service it unless you've got an extender card which plugs in place of the module and then rises it up out of the test set so that it can be analysed and tested. But even so, you need then to have all these extended leads for the jumpers, for the RF, SMB and SMC sockets and plugs, so you've got to have those handy as well, and it makes it quite difficult. And that's one of the things, gripes that I've always had about Rhode Schwarz, is that it's built to have the modules replaced as well, rather than having the modules repaired to component level. And I've just had a brief look at the service manual before coming to this section of the video, and it quite clearly says in several sections in the video, in the manual, that when you've tested, say, the RF attenuator, which lies up here, the output signal from that is fed to the RF converter module. It doesn't give a diagram or any information for the RF converter module, so it recommends that if that's failed, then, you know, to have it returned for a new module to be replaced. Some modules are repairable on this, it does tell you that in the service manual, but there's some modules that aren't. So it doesn't give you any info on them. It just says basically if that module's not reading right, you know, test here, test there on these jacks by unplugging these RF leads and connecting spectrum analyzer, and you test spectrum analyzer. If that level's wrong, that module's failed, so therefore send it back to Rhode Schwarz for repair, you know. And again, you know, that's very much from my standpoint a negative, because it prevents further repair of the instrument. And naturally the price point for having that repaired at Rhode Schwarz would be thousands and thousands of pounds or dollars, etc., to get that done. So, you know, it's makes it uneconomical for someone who's purchased the instrument second hand, for example, to have it repaired. Unless, of course, there's something obvious and we take the lids off and, you know, a module, and then further analyse it and see whether we can reverse engineer it to find an obvious fault, maybe. But that may be quite rare. You know, it's often the case that sometimes there's components in there, especially with it being Rhode Schwarz, that are uniquely manufactured for this test set alone, and therefore some specialist hybrid amps and things may not be available on the common market. But anyway, we're jumping ahead there, so let's see where we get with it. I wanted to check the power supply first. It looks like as if these three electrolytic capacitors could be wrong. Haven't looked at the manual fully in depth yet, but this power supply section in the rear, these could be the supply lines then to the rest of the instrument, with them being electrolytic caps soldered on. It looks like it's some rail, so it may be that we drop on with easy testing of that, but I'm going to look in the service manual and find out where we are with that, and then we can start doing some RF tests from there if the supply lines are correct. So we'll just have a look at that now. Okay, so we'll just check some voltages in this general area here. I can see it marked on the board, for example. Maybe it says something like there, minus 12 and plus 12. So we've got that's like the plus 12, I think it is, and it says yes, plus 12 volts on the meter, so we're definitely getting that, plus 12 volts. that line there. Although that light's in the way. And then a bit further up is the minus 12 volt line, which is this one here. And we're not getting anything on that. Nothing at all on that. So that's a bit strange. Then we've got the 5 volt rails as well. If we go right in, for example, it might be that we can get it to focus. So that's the plus 12, which we've just been on. And we're getting a voltage there. On my meter it says 12.02 volts. The minus 12, that doesn't have anything on it at all. It's just noise. But there again, it might be the ground reference point. So I'm not going to jump to any conclusions as yet with that, because we're on chassis ground as a reference. It might be that there's another ground reference for the negative rail, but we'll check that out in a moment. Then we've got a plus 5 volts. Yeah, it's reading 5.22 volts. Further up as well, let's have a look. There's those caps somewhere around here. There we are, look. They're all on the same supply rail anyway, so we can go on to those. I think there's a 12 volt rail as well for standby voltage, but I'll check that. So we'll just go on to there and just check that, see what it says. Yeah, 5.2 volts, so that's okay. I think that was this rail, 12 volt standby. But yeah, that minus 12 volts isn't working, so that's interesting. Minus 12 and plus 12, difficult to see on the board. There you are, look. That might be able to give it a bit more clarity, but we're not getting anything on the minus 12 for some reason. I don't know why, but yeah, just about 60 millivolts of noise. However, on the plus 12 volt line, we are actually getting 12 volts DC nicely. So it's just this minus. I just need to find out why that's not working. Now, according to the service manual, it says in the service manual, and I can get it to display again, it says there's a plus 5.2 volt rail, a minus 15 or minus 12, a plus 12, a plus 5 volt rail as well. So it basically says that. And it says that check the supply check LED on the power supply lights up with the power switch on, switched. So it looks like as if we take the lid off the top of the instrument, then it will be obviously apparent that, yeah, there'll be a power supply module with the LEDs in the top. So we'll have a look at that next. Well, according to the manual, there's some this is the power supply here. It looks like it's made by Ascom, I think it is. The label on the other side says Ascom on the power supply module. The service manual makes reference to some LEDs that show you what the supply lines are, but there's absolutely nothing on this. And I'm finding with this service manual as well that I've got, that it appears to be written for an older model of this, an older version should I say. Same model number but an older version, and there are some slight differences that I've noticed already. So, like for example, the plug references on the motherboard don't match with what it says in the manual, and I think it's because this is a newer version of the spectrum analyzer, whereas the manual reflects an older version. So yeah, so there you go. But right down here in there, that plug with the multi-core cables on it there that you can see, that's the actual power supply that connects into the motherboard beneath. So I'm just going to check my supplies there, but it might just be me on the wrong ground reference point. I would have thought if we'd lost the minus 12 volt rail we'd have a lot more problems with it than what we currently have now. So, but one never knows. So I just nearly sawed my fingers off by touching these fans, so that's something to be a bit wary of. So yeah, we'll just go into it. The RF attenuator for the input is there. That's the module for the RF input. Floppy disk, 2 fans, and then the power supply module sits at the top here, and there's a cable then connects down to this board here, which then distributes the power. So just flip it back up now and see whether we get onto that socket and measure some voltages. Okay, well the plot thickens. We've got that socket up here which is residing there, so that appears to supply one lot of supply voltage for this portion, which tends to be around the plus 5, 12, plus 12, minus 12. However, in this section here there's another socket which this cable connects to, and that's the supply to all the modules, which is what it references in the service manual actually for doing the checks, which is the 15 volt rails and the plus 28 volt rails, which we'll check. But what I did manage to find, just on this quest of not being able to get the 12 volt, minus 12 volt rail there, is that what's strange about it is on that, see if I can get on it, on that line there, these are all plus 5s, as you can see on the display, if it's showing it yet, plus 5 volts. There we are. So that's 5 volts there. They're all 5 volts, plus 5. Again, that's another plus 5 when it comes up. This slow ass meter from Fluke. It takes it half an hour to calculate what voltage is there. Plus 5 again. This one here at the top I think is the minus 12. So when I go on to that, if I get on it, without slipping off it, just got like noise on it and crap. That then is the plus 12 I think, or minus 12. That's plus 12 volts, and that there is also plus 12. So I think this one here is the minus 12, but I could be wrong, Anyway, further down as we go down to here, we've got then the supply for all the modules, which is what the service manual asks us to look at, which is obviously, as you see there, we've got a plus 5 volt rail just there. That's a 5 volt rail, this track there going down there. We've got a plus 15, minus 15, plus 28 volts. So if we check those a second, let's have a look, see what we get. Right, I've just got to move my magnifier because I'm viewing this from quite a way away, so I just don't want to I want to make sure that I don't short anything out and then obviously blow it up. So we're getting 5 volts there, which is good. The plus 15 volt rail, that's if it's going to come on. Yeah, plus 15, another plus 15 I think. Yeah, then we've got minus 15, which is this one. That's minus 15, which it's working, and then plus 28. Plus 28. So they're all there. So I think it's just this great mystery of the of the minus 12 volt rail, which appears to be missing. So but that could be down to my measurement. It may be that that's got to be from a different ground reference point, which I've failed. Obviously I've just connected the probe to the chassis and then obviously metered it, and it can be quite often the case that for some switch mode power supplies certain rails are isolated from common ground, and it could be that there's a 0 volt reference for the minus 12 volt rail, which I need my probe connecting to my negative side. So I'm not going to go too in depth on that because I'm fairly confident that if a minus 12 volt rail wasn't there, then we'd be getting a lot more other errors, and it would be obvious that the minus 12 wasn't there, let's put it that way. Plus as well, it will come up with, as part of the self-test routine, major failures with multiple modules and down to the supply rail being missing. So I'm 99.9% confident that the minus 12 volt will probably be there, but I might come back to it later on. You see, the problem is in the service manual with Rhode Schwarz, it doesn't give a schematic diagram for the power supply. It just basically says return it back for repair. It doesn't go into great depth about where the supply lines come and go from and to, and it basically just says test this module at these test points, and if it doesn't work, just send it back to Rhode Schwarz, you see. So there you go. Right, so we'll move on now to doing some RF measurements because I can't find any additional detail on the minus 12 volt rail in the service manual. It just basically doesn't give you any help with that. So I think we'll just have to, obviously the main supplies for the RF modules is on this connector, and that doesn't employ a minus 12 volt rail anyway. So I think the minus 12 volt rail is probably just used for the external VGA and some other features that are on the instrument on that motherboard. They may go off to other sections of the digital board, for example, but as I say, I can't find any indication that that's missing as far as the system's concerned. But yeah, I can't measure it on the meter at the moment. But we've had this before with the Marconi 2955B repair video I did there. We had a very similar thing where we had the ground probe for the meter connected to the non-isolated ground, and that then meant that the measurement was inaccurate. It didn't read the supply because it's obviously needs a ground reference for that minus 12 volt rail. So it was there, but it just turned out we couldn't measure it, so we just had to move a ground probe onto the right spot. Unfortunately in this case, because service manual gives very little detail as to where that is, then I'm not going to go any further with it. So we'll just carry on with some RF measurements. Just further on the power supply a second, I've read some information on the service manual from Rhode Schwarz regarding the power supply, and it just basically talks about the checking the 15 volt and 5 volt supply rails. It doesn't even mention the 28 volt rail actually, which is strange, but what it doesn't mention is any of the 12 volt rails. So it talks about that only, which is strange. Well, it makes me wonder now whether on the motherboard of the instrument there's the core voltages which we had on this connector here, the plus 15, minus 15, plus 5 and 28, plus 28 volts. Once it's fed to this board, then there's somehow perhaps maybe a DC to DC converter, one of those recon modules or something like that that's on the board that maybe then gets the minus 12, because there's no reference I can find, and I've had a real good look through the service manual before coming to this section of the video on where the 12 volt rails originate from, and there's no information at all. So it could be that that's generated on the actual motherboard. There's a component on it which is a DC to DC converter, one of those little modules, and it sticks out multiple supply rails of plus and minus 12 volts, etc. So yeah, it's a bit weird is that. I just hope that it's not a major thing, but I can't seem to get any info, you see, so as to where that's coming from. But anyway, all the module diagrams all seem to just indicate those supplies on the physical diagrams themselves. So I'm struggling at the moment to get some more detail from the from that. I wonder if the 12 volts is actually from an onboard regulator whose input supply is 15 to start with. So for example, the in this case down there, the minus 15 supply, which is this pin here, that minus 15, maybe that goes to a negative voltage regulator which is soldered on the board somewhere, the motherboard, and that then produces a minus 12 volt supply, and likewise a plus 12 volts is a derivative of the 15 with, say, a common classic voltage regulator 7812. So I'll investigate that as well, but yeah, it looks like as if we can't pick up that minus 12, which does concern me, to be quite honest. But as I say, had that supply been missing, I would have expected a lot more self-test failures than we've had. And incidentally as well, the self-test failure, the code that we had earlier when we did the self-test, I can't find that code anywhere in the service manual. As a matter of fact, there isn't a table in the service manual which displays the fault codes. So again, that's quite poor. There's nothing in there at all about fault codes. It just basically says that you know, if this particular test function fails, then it's basically return the module back to Rhode Schwarz. Doesn't give you any further detail as to where to look or what the possible cause could be. It just pins it down to a particular module and then says, yeah, stick it in a box and return it back, and we'll charge you, you know, thousands of pounds to fix it. So yeah, a bit tricky this one, I'm afraid. Okay, so onto the block diagram of the instrument, or certainly the RF section anyway. If we look here on the top left hand side of the diagram, we've got the RF input socket, which is on the front of the instrument where we connect our signal to be measured. We've got the RF attenuator module, which is that little module that I showed you earlier in the front, just buried behind the connector. We have a connector that feeds in an external signal source for calibration purposes, which is actually 120 megahertz at minus 40 dBm according to the information in the manual. And this is fed into an RS switch, which is integral within the step attenuator module. The step attenuator module is this entire square here, and inside this step attenuator, which I'm going to show you further breakdowns shortly, we have multiple pads inside that are switched in and out with relays, and basically depending on what configuration we set on the instrument's RF input attenuator level, it will select the appropriate attenuation, and then the signal will be passed out then to the RF converter module. So basically the calibration sequence, when we press the self-test, self-cal, that injects a signal into here, and this little RS switch flicks over to the calibration standard to then measure it through. In doing so, it will set this attenuator to, I think it's 0 dB or whatever attenuation it selects, so that that minus 40 dBm is more or less passed straight through to then be read by this RF converter module. And that's where it will either pass or fail it, because if a module, the RF level coming into the module is too high, too low, whatever, it'll then fail that test, which it is doing obviously. So it makes me wonder if there's a problem with the RF attenuator module. So reading the service manual, it seems to indicate using a scalar network analyzer in my case, or a spectrum analyzer with TrackGen, to basically sweep this module and then use the user interface on the front of the spectrum analyzer that is faulty, then obviously to ramp up and down the ranges, the switchable ranges that this attenuator can provide, to then check that that's correct. Because obviously this is burned out, this part of the attenuator, or something's happened to it where it's not switching properly. The RF level coming through from the calibrator won't make it through in the correct level, so therefore it'll error it. So we need to just look at this now in more detail, so that's what we'll look at next. Okay, just to explain the measurement so far then. We've got the Marconi Microwave Test Set on, which we are set a sweep frequency from the RF output port, the purple cable, being plus 10 dBm signal level, from 10 megahertz to 7 gigahertz, and we've got the scalar probe, which is the grey lead on the left, connected to the scalar sensor, the Marconi scalar sensor. That in itself is connected then to the output of the RF attenuator, step attenuator module. So this solid coaxial cable here goes to the RF converter module directly from the output of the step attenuator. The scalar sensor is connected to that, and basically we've done before doing this connection, we've done like a calibration just to make sure that the loss of the cable, this purple stuff, Anritsu, it's quite a long cable, a good 2 meters. At that frequency, it's, you know, it can be a bit lossy, but I think it's rated up to 18 gigahertz, this cable. These SMAs are all torqued up. Anyway, we've broken it out now onto a screen so that we can look at the response. So this is the response there. I can straighten the camera up if it stops moving, which would be nice if it did that just for once. Right, so we've got in the top left hand corner, just here, we've got the marker, which is down at 10 megahertz here roughly, and it's reading plus 9.27 dBm, where our actual power, the output power, is set to plus 10 dBm. So we've got about 0.7 dB of a loss just in the cable alone, which is to be expected, plus whatever internal losses there are in the RF step attenuator module. Now if I adjust the marker, if I can get the marker to show on this thing, let's have a look. If I can do that. Markers, right, so if I move that, it goes down to about 8 dBm level at 1.53 gigahertz is the frequency, and then we're talking about 7.6 down to about 6 dBm at about 7 gigahertz roughly. 6.5, 7 gigahertz. So that could be down to the cable. Obviously there's a mover cable about, it's not making much difference, but there's 2 meters of that cable. I might try and shorten it a bit later if it gets serious, but that's showing quite a flat response really, with slight variation in it, to be expected really due to length of cable, etc. Now at 120 megahertz, which is where the calibration signal takes place, is roughly about here. 120 megahertz is roughly about there. I can't sort of get it bang on 120 megahertz, but 114, 132 megahertz, I think that is. So it's reading, you know, we've set the attenuator on the front of the Rhode Schwarz spectrum analyzer to 0 dB attenuation. So basically it's in pass-through mode. You know, whatever signal is coming in on this connector basically goes straight through to the output without any attenuation. So what I'm going to do now is I'm going to adjust the attenuator to see what happens, and let's take it from there. So if I adjust it, that's 10 dBs of attenuation, and it's keeping in line with that. If we go to the marker, just a second, where is it now? Let's put that back to 0 dB a second. Right. So bearing in mind the signal that we're putting in isn't 0 dBm, it's plus 10 dBm. So the signal that's coming in that we're measuring is plus 10 dBm. So we're measuring plus 9.34 dBm, which is in the red box right there, just there. So as I adjust the attenuation now, so that's 10 dB attenuation according to the front of the Rhode Schwarz spectrum analyzer. So that's now reading 0.68 dBm, which is fine. The next level of attenuation is 20 dBm, so that's minus 10 dBm on the scalar analyzer. The next one is 30 dBm, so that's minus 20 on the red box, which is correct. The next one is 40 dBs attenuation, so that's minus 30, because don't forget we started with plus 10 dBm minus 40 dB is minus 30 dBs attenuation. And then we've got 50 dBs of attenuation. It's reading 40 dBs there, which is correct. And then I think we're going to get down into noise floor. I might have to use the spectrum analyzer for a better dynamic range, because this tends to fade out around about neg 60, neg 70 dBs. So then we're in the noise floor then with 60 dBs of attenuation. So that sort of reached the limits of the scalar network analyzer. So we're talking minus 48 dBs there, and it says minus 60 because that's in the noise floor. But at least it shows us there that the step attenuator, particularly on the put 0 dB back in, we're back to plus 10 dBm nearly, that works. So it looks as if a step attenuator is fine. Yes, it does have a slight drop off, but only a couple of dBs towards the end of the attenuation cycle on versus frequency. When it gets to the top end, the 7 gigahertz-ish frequency, so it drops off a bit, but that can be calibrated out anyway as part of the calibration of the instrument, and that's to be expected really. And the other thing is that the cable itself is excessively long that I'm using in this experiment, but at least we can see that the RF attenuator module is functioning properly. For the extra attenuation steps, the ones where we just can't see it, which is the last two steps, which is from there's one more step and then another one. I'll use the spectrum analyzer on those last two steps to see what the attenuation level is on those. Okay, so we're using the Aeroflex spectrum analyzer. This has a greater dynamic range than the scalar probe that we've just been using on the MTS. However, it has a less of a frequency range. This has 1 kHz to 3 GHz bandwidth, but it's better than nothing. So what we've done anyway, we've joined the purple cable and the silver cable up, the track gen out and the RF in together, and we're going to calibrate the instrument. We've used a joiner, an SMA to SMA joiner, because we've got about, I don't know, 3 meters of cable here, something like that. So what we'll do is we'll set up the frequency, and we'll put the start frequency in at say 10 megahertz, and we'll put the stop frequency in at we'll leave that at 3 gigahertz. We'll then go over to source, we'll put the track gen on, put the tracker on as it says there. We've got, let's just make sure these cables are nipped up, which they are. We'll normalise, so that straightens that out. The RF level, let's have a look now. Markers, marker, so that's 0 dBs, which is highlighted in the right hand corner there. So that's marker 1 across that frequency range of 10 megahertz to stop frequency 3 gigahertz. So we can just verify that by looking at that a bit closer. So there we are. So that's all okay. So what we'll do now is we'll look at the same measurement again that we're doing before, but this time what we'll do is we will connect up the track gen output to this port, and then the socket on the back of the step attenuator will connect to the input then at the spectrum analyzer. and that way then we can do some measurements, sweep it and get better dynamic range. Okay, so we're using the Aeroflex spectrum analyzer. This has a greater dynamic range than the scalar probe that we've just been using on the MTS. However, it has a less of a frequency range. This has 1 kHz to 3 GHz bandwidth, but it's better than nothing. So what we've done anyway, we've joined the purple cable and the silver cable up, the track gen out and the RF in together, and we're going to calibrate the instrument. We've used a joiner, an SMA to SMA joiner, because we've got about, I don't know, 3 meters of cable here, something like that. So what we'll do is we'll set up the frequency, and we'll put the start frequency in at say 10 megahertz, and we'll put the stop frequency in at we'll leave that at 3 gigahertz. We'll then go over to source, we'll put the track gen on, put the tracker on as it says there. We've got, let's just make sure these cables are nicked up, which they are. We'll normalise, so that straightens that out. The RF level, let's have a look now. Markers, marker, so that's 0 dBs, which is highlighted in the right hand corner there. So that's marker 1 across that frequency range of 10 megahertz to stop frequency 3 gigahertz. So we can just verify that by looking at that a bit closer. So there we are. So that's all okay. So what we'll do now is we'll look at the same measurement again that we were doing before, but this time what we'll do is we will connect up the track gen output to this port, and then the socket on the back of the step attenuator will connect to the input then at the spectrum analyzer, and that way then we can do some measurements, sweep it and get better dynamic range. Okay, so I've set a 0 span up basically on a spot frequency just so that I can just check the level. So that's if we press 0 dB, so we basically got 0 dBs in the top right hand corner there. It's quite uniform obviously. I'll just adjust the attenuation ranges now. That's minus 10 dB step, that'll be a 20 dB step, 30 dB step, and as we can see in the display, that's what we're getting in the top right hand corner just there. Next step now would be 40 dB step, then we're getting into the noise floor a bit, and obviously then we would have 50 dBs, but we see we're getting into the noise. Now if I go to amplitude and I select amplifier, internal amp on, that might help us. And then next stage, so we've got, so if we go right back up to the top again, and then 0 dB, right, so then we're looking at 10 dBs, 20 dBs, 30 dBs, 40 dBs, 50 dBs, 60 dBs, and then the last step, which is 70 dBs, but that's well into the noise floor. I might be able to resolution bandwidth if I can get to that. Don't know if I can access that while I'm in the track gen mode. I think you can't, but I could be wrong. Resolution bandwidth, I can't see it, so it may not be there. Zoom in, but no, it doesn't appear to be available in this mode, not that I can see anyway. Sweep, Sweep time, no. But we've got a very good clear indication there that the step attenuator is fully functioning, and obviously that proves that it's not the step attenuator that's at fault. Okay, so now we're going to look at the calibrator, which is this coax here, connects into one of the lower ports on the spectrum analyzer's RF attenuator module. The top port connects to this solid coax, which is a signal output, which is then fed into the down converter, up converter module. But this here is the calibrator. That, according to the service manual, is the service manual says neg 40 dBm at 120 megahertz. So we've got that coupled out now to the spectrum analyzer, and if we can just faff about with the spectrum analyzer so it reads the right level. Now it only comes on momentarily, so I might have to do some magic with trying to set up the spectrum analyzer. So we'll just go to frequency 120 megahertz. We will set a span of 1 megahertz. We will then let's have a look at the RF level. Oops. Put that 1 megahertz amplitude. Oh, there's something there already. Got minus 20 dBm, minus 30. I'll leave that at 0, at minus 10 dBm. And what we'll do, we'll set the marker up to measure 120 megahertz, bang on, which is that there. Got it like it says in top right. Then we'll go to trace and we'll select max hold. Now then, what I'm going to do now is I'm going to set the spectrum analyzer under test, the Rhode Schwarz one. We're going to press the calibrate button. Oops, press the preset button already. Right, calibrate button, and then we'll press the normal calibrate short one. So let's see what it reads. There we are, look. So it's just gone through its calibration routine, obviously failed it, but important thing here is we've got a measurement, a snapshot of what's just occurred. And as you can see there, the frequency accuracy is correct at 120 megahertz as per this measurement here, and then the level is minus 40 dBm. So the calibration, the calibrator, is fully functional. It's obviously giving the correct output level at the correct frequency. So it's not the calibration signal that's at fault. It's so we've already found two things now. The RF module, the step attenuator is fully functional, and so is the calibrator reference signal. That's fully working. So I'll just do that again actually, if I can get it to work again. Let's have a look. Trace, max hold. Let's have a look. Don't know how you get it to view, min hold. How the hell do you get out of it? I've no idea. A, B, C. What's that? Clear. There we are. Right. Okay, max hold again. Go to calibrate, and then hopefully, there we go. So minus 40 dB. So yeah, it's consistent. So let's just clear that again. Let's try it again. Yeah. So that's what happens if I don't max hold it. It just comes on momentarily. If I just clear that and do it again. There we are. So, interesting. So what I'm going to do now is I'm going to plug it back onto the, I'm going to test that module, switches it now internally, because obviously the calibrate signal's coming in on the bottom, it's going through the RF switch, coming out on the top. So I just need to connect the spectrum analyzer now to the top socket. This calibrator signal back on the bottom. Just check that it switches a path through properly on the RF attenuator module. Okay, so I've connected the calibrator back into the module, the top. Now the signal lead off back to the converter module is from the top, so that's going back to spectrum analyzer. So we'll run through the routine again, this time now checking the internal switching path of the RF attenuator module. So we'll just run that again. I'll not bother putting max hold on at the moment, just see what yeah, that's there, look, -40. Right, I'll put max hold on now. I could clearly see it were there anyway, but just for argument's sake, I don't know what that is. That looks a bit of spurious crap. Let's just have a look. Clear it. Max hold again. Seems to be switching a bit erratically, as you can see there. It's not quite clean, is it? Let's have a look. Just clear that a second. Let's see what happens now. It might just be the time capture, because it does look like as if it's quite cleanly switched there. So we'll put the max hold back on again, and then we'll just do it again. Yeah, it's there. So the frequency is stable, and so is the marker with the -40 dBm reference level. So that proves that the RF step attenuator module is functioning perfectly. If it wasn't, then we wouldn't be getting that level, and it wouldn't be switching it through it. So it looks like as if his fault's more serious than first fault. Then it might be more to do with the up converter, down converter RF module, the converter. And in which case then things might start getting a bit tricky. So looks like we're on with that next. See what the manual says. Okay, so what we've done now, we're going to try and con the instrument by feeding a calibration signal directly into the RF module, bypassing the RF attenuator module. Now in order to do that, what I've had to do, I've had to compensate the signal generator for the level difference that we had earlier in the measurement, where we were reading about, I think it was 35 dB below the actual level we were injecting in on the front socket. So what I'm going to do is I'm going to try and con the instrument into believing that the calibrate signal is at the correct level, because obviously although we're injecting 120 megahertz at -40 dBm, in actual fact the instrument's reading about 35 dBs more loss than is actually present. So we need to compensate for that. Hence the reason why I've had to set the signal generator to +16 dBm in order to make up for the differences between the measurement levels that we were receiving earlier. So what I'm going to do now is I'm going to, now that we're injecting that 120 megahertz signal in, which would replicate the signal from the calibrator, now I'm going to go to the calibrate menu. Bearing in mind it failed this earlier, so let's see whether this sorts it out. Okay, right, well, we're getting a lot further now than we were before, so it's going through some kind of a calibration sequence, or trying to. So again, that does prove then that it is a level issue, the fact that it's now trying to go through some kind of calibrate sequence, and which is the cal short. It may also find other errors, which no doubt it will do, because of the fact that the levels are all out of kilter anyway, and its own modules with the look of it. But at least that proves that it's sort of a level fault, really. So that's strange, very strange. But at least it's managing to do some kind of a cal short, which I gather takes up to about 5 or 6 minutes or something for it to complete. But that's the test that I wanted to prove, but it got past that initial lockup of not being able to obviously get past the calibration stage with the frequency and the level. So at least that proves that it's a level issue now, and then we can move forward with the next test. Bearing in mind as well that that level test that we've just done with the calibrator, where we injected the signal directly in, that had to take into account the fact that the default level setting on the RF input is plus 10 dBs. It also had to take into account as well the fact that the reference level was set to its maximum attenuation level, as well as the input attenuator, because there is a further attenuator that's actually on the RF converter module, according to what's in the service manual obviously, which sets the fine attenuation limits between the 10 dB step attenuator, which is behind here on the end. So we've had to trick the instrument by putting a far higher level in, although when we feed a signal in here it's reading 35 dBs below what it should be or whatever. In actual fact, when injecting signals in directly into the RF converter, you have to then calculate all the differences between the 10 dBs being lost, that attenuation, then you have to also make sure that you compensate for all the other offsets that are in the system before you feed that signal in then into the RF converter module. Hence the reason why it didn't take the calibrate signal that we were putting into it and start to measure it. So that's something to be aware of when you're trying to inject signals directly into modules. Later in the system stages, they have to overcompensate for those attenuation pads that are in there at the start of the components, which is here. And obviously, you know, if you don't get that right, then the level that the RF module will be expecting will be off anyway, and obviously it won't work. So you have to take into consideration that now the microcontroller in this test, in the spectrum analyzer, takes account of what the attenuation steps are here and what the RF attenuator fine-tune levels are as well. So you have to take all that into consideration when you're inputting the cal signal, otherwise it could make a mess of things. Okay, just a bit of background information regarding the functional description for the RF attenuator, step attenuator. It says the module consists of 3 switchable attenuator pads, 10 dB, 20 dB and 40 dB, and a switch used for switching the internal calibration generator to the RF input. The switches are bistable and are switched by a short pulse through a driving coil. Following the switch over, the current through the driving coil is switched off. The control is affected by the level transducer via the serial bus. The board contains the EEPROM as data storage for the frequency response correction, which is read when the instrument is started. See, on this there is also a pin diode attenuator on the RF converter module, which can attenuate between those steps. When you adjust the rotary control on the front of the spectrum analyzer and you turn this, between the 10 dB steps, the fine attenuation is done actually in the RF converter module, rather than obviously there. That's just switching in fixed steps. So there could be something wrong with that as well. But anyway, we'll have a look and see whether we can feed a signal directly in on this coax now, and from a signal generator, and see what the level is then when the front is, the RF input is set to 0 dB, and then that way then it should read the correct level, but obviously it won't, because we proved that the RF attenuator, step attenuator, is fully functional. Okay, so what we've done, we've connected our friendly signal generator 1 GHz at 0 dBm on this purple cable into what was the input of the up converter module, RF converter module. We're bypassing the RF attenuator switch. What we've just done off camera is set the we've set the screen to show now 0 dB attenuation. That's so that the calibrated DAC levels that are already in the instrument's memory take account of the fact that we've got 0 dB attenuation expected to be on the input. Now, although the RF attenuator module that sits behind here has totally been disconnected, as far as the computation of the measurements concerned, the instrument needs to know that it's set to 0 dB input attenuation, so that it can set up the fine attenuation then at the RF front end module that sits behind the RF attenuator, the up converter module, to expect that level, because obviously there's two lots of attenuation going on. There's a variable attenuator which is affixed to this variable attenuation between the physical fixed steps of the RF attenuator, and the variable attenuation is done using a pin diode attenuator in the up converter module. So I've had to tell the computer basically that we're now expecting a 0 dBm signal, well, an unattenuated signal anyway. So it's capable of reading up to plus 33 dBm on the input, so we're okay, we're in a safe range. So if I go center frequency 1 gigahertz, and we've obviously got a level coming in. If I change the span now to 1 megahertz, and then we've got a level, if I go to marker, normal, and the level of the marker is reading minus 35.72 dBm, which is as you can see there. So it's reading 35 dBs out, because the signal that we're putting in from the signal generator is actually 0 dBm. So this now proves that the RF converter module, which sits here, the second module in down there, has got a fault on it of some description. So we're going to have to look at that now in greater detail now that we've proved that fact. Okay, so back to the block diagram now. We've proved that the RF attenuator module step attenuator is functioning. We've checked the calibrator level itself independent of this module. We've then checked the independence of the attenuator pads all the way through and the pass through at 0 dBm. We've also checked that the calibrator path manages to get through the module back out onto this socket here. So we've now eradicated this from our thoughts, and we're now over to the RF converter module. Currently we're feeding in a signal in the last measurement into this socket. We've disconnected this link here, and we're feeding a signal in directly there at 0 dBm at 1 gigahertz, and that frequency is entering the RF converter module, and now it's being analysed within the context of the measurement and displaying an incorrect level of minus 35 dBm when it should be reading 0 dBm. So obviously there's a problem with this converter module. Now if I look at further detail on here, we do have not too much information at this level, but basically we've got some kind of local oscillator being fed in here, which is obviously then producing an IF. So it converts that frequency that's coming in, mixes it here, and then with amplification we've got a bandpass filter, some kind of filtering arrangement going on before it's then fed into another mixer. It looks like as if there's some kind of a second local oscillator being fed in here, so remixed again a second time to produce a second IF via another bandpass filter, where the higher component looks like a low pass, whereas this looks like a band pass. Higher and low frequencies are rejected while the fundamentals pass through for mixing. It's mixed a second time obviously, and then the higher frequency components are removed, allowing the fundamental to come through. So we're going to have to look now at the next section to see where we are with measuring these levels on these sockets, to find out whether it's something external at the RF converter module or whether the fault lay within this RF converter module. So that's where we'll go next in the manual. Okay, some bedtime reading. So we know about the RF attenuator, we've read about that before, and it talks about being switched from 0 to 70 dB in steps of 10 dB, and it rattles on about 120 megahertz calibrator signal, which is in close tolerance to minus 40 dBm for calibration purposes, or 0 dBm for the self-test, which we ran early, if you remember, the self-test, and it also failed on that as well as a calibrate. So now on to the next module, which is what we're looking at now, the RF module. The RF module provides for conversion of the RF input signal to the second IF at 741 megahertz. and for generation of the required first local oscillator signal, 2 microwave units are provided for the RF circuits. The RF converter contains the circuits for RF signal processing, filters, mixers and amplifiers. The YIG sampler contains generation and distribution of the first local oscillator signal, and the sampling mixer for synchronization of the first local oscillator. In the RF converter, the input signal passes via the input low pass to the first mixer. The low pass at the mixer input provides for suppression of the image frequency, image equals local oscillator plus IF, such that the conversion remains unambiguous. In the first mixer, the input signal is converted to an IF of 4341.4 Megahertz by means of the first local oscillator, 4.341.4 gigahertz and 7.841.4 gigahertz. The mixer is followed by a low noise IF amplifier, which compensates for the loss due to mixing. The signal then passes a filter with a 3 dB bandwidth of approximately 50 MHz for filtering the first intermediate frequency. Subsequent to the IF filter, the signal is converted to the second IF of 741.4 MHz in the second mixer. The local oscillator for the second conversion is supplied by the second IF converter module. The conversion loss of the RF module is approximately 8 dBs. So then we've got the second converter. The second IF converter module is used to convert the second IF to the third IF of 21.4 MHz and for generation of a second and third local oscillator. The module has 2 inputs for IF signals which can be selected using a changeover switch. The signal from the RF converter is first amplified by approximately 15 dB. The input switch for selection of the input signal is then connected into the signal path. A power divider is provided for further processing of the IF signal with the full bandwidth of the RF converter. One output of this divider is amplified and provided as module output. The second output leads via an amplifier to a resolution filter. If the resolution bandwidth is set to 10 MHz and it suppresses the image frequency, which might occur with the third conversion, the filter is followed by a third mixer, which converts to 21.4 MHz. The local oscillator for the third conversion is obtained using an oscillator which is synchronized to the 120 MHz reference of the FRAC-SYN. The signal of this VCO is also used for generation of the second local oscillator and as a reference. The second local oscillator is generated by multiplication of the oscillator signal and filtering of the comb line. The conversion gain of the converter is typical 12 dB. The level in relation to the input mixer is approximately plus 4 dB. IF filter. The resolution filters for bandwidth between 1 kHz and 5 MHz are located on the IF filter board, with 10 MHz bandwidth and filter stages of the module are bypassed. Crystal filters are used for bandwidths from 1 kHz to 30 kHz. LC filters are used for bandwidths of 50 kHz or above. The individual modules of the FSE family are supplied with 2 different models of the IF filter boards. The models 20, e.g. FSEB30, provide 4 filter stages. The models 30 provide 5 ones. The individual filter stages are being decoupled from each other by means of amplifiers, which is why they act like a Gaussian filter. In comparison to other types of filter, the Gaussian filter provides minimum settling time. The 2 models of IF filter accommodate switchable IF amplifiers, step gain, and 2 independent calibration amplifiers subsequent to the first 2 filter stages. The step gain can be switched in 0.1 dB steps from 0 to 50 dB and used to increase the signal on the reference level in spite of different levels at the input mixer. Amplification of step gain equals minus 10 dBm, which is the mixer level. One of the two calibration amplifiers is used to compensate for the deviations of amplification with different bandwidths or step gain settings. The amplifier is controlled via the serial interface at the level transducer and the DA converter on the IF filter board. The second calibration amplifier is controlled by an analog voltage, which is modified by the frequency transducer during the sweep according to the frequency response of the input stages. The module provides two outputs which the filtered third IF is applied to. The output level in relation to a signal on the reference level is 0 dB. As long as a step gain can be adjusted, mixer level below neg 60 dBm, one output is connected to the rear panel, the second one to the digital IF board, where bandwidths of between 10 Hz and 1 kHz have been realised. In parallel, the logarithmic value of the IF signal on the board is determined. The log module consists of an integrated series connected rectifier which provides for a dynamic of 90 dBs in the modules 20 and 110 dBs in the modules 30. The generated video signal is applied to a 20 MHz A to D converter on the detector board, where it is looped through the rear panel. And then it goes on to talk about the detector board and all the other bits and bobs. So it's quite clear that it's different on different models, being the 20 or 30 model FSEA and FSEB series spectrum analyzers. So they're the variances between them. So we'll have to look now at the section of the service manual that talks about how to test the RF converter module. Just for reference, I know we've talked about this before, but I've just come across this diagram of the RF attenuator module and what it looks like internally and how it's configured. I only show this now because this service manual is about 1,000 pages long, and it takes about 1,000 years of burning your mouse out trying to go through all the pages to find the relevant section. But anyway, eventually I did find it, like I said I would do earlier. But as I say, it takes such a long time going through this manual. But that's the RF attenuator module. We've got the RF input coming in from the front there, as referenced by X1. These are obviously the arc relay contacts and the electromagnetic coils. The relay coils are above here in suspension. They have plungers, mechanical plungers, that alter these vertical and horizontal sliders. And then beneath we have resistors. These are probably made up of like a substrate, metal oxide, semiconductor type, well, it's not a semiconductor, it's a resistive material embossed on like a glass tile. It's like a metal oxide semiconductor, well, metal oxide resistor elements. And these are basically etched out on little PCBs, which are put in, or surface mount resistors in some case, but Rhode Schwarz tend to do it more fancier than that. We've got a 50 ohm termination resistor there, probably for the setting it between 50 ohm and 75 ohm nominal impedance, depending on that's in or out. And this is a calibrator signal coming on an X2. That comes in 120 MHz at minus 40 dB, and obviously when we hit the calibrate button, it then literally clamps down all these horizontal looking connectors to be passed through all the way through to the RF module that then we're now going to be looking at. But obviously when we're not calibrating, this vertical slider here would come away, and then depending on what attenuation we've got, so if we've got like a 10 dB, a 20 dB and a 40 dB pad, it'll then clunk in and out the appropriate pads to get that level of attenuation, as we looked at earlier. So that's like the sort of schematic diagram of the RF attenuator, rather than the block diagram fiasco we were looking at earlier, but at least it explains it more clearly there. Okay, so where we're at now, we're into the troubleshooting section of the RF module. Now the RF module is this beast here, and it starts basically from where the RF signal comes in, which is obviously from the RF attenuator. It arrives in a socket there, and that's the whole of the module right the way down. Now obviously, as part of this troubleshooting section now, we now need to look at the signals that are given into this for mixing from the YIG oscillators, and also from local oscillator inputs as well, to check to see whether those levels are correct. And if they are, then it would appear according to the service manual that if these tests reveal that there isn't an issue with the levels coming into this module, then this module is at fault. And the manual quite clearly says that if there's a fault, that it should be returned, because it says there, it says repair the RF converter module is not possible. It is replaced in the case of an error. And then it waffles on about these sections here then, obviously, to look at that. But it does say an excessive attenuation can be caused by a fault in the RF converter, which is a situation that we've got, obviously inputting 0 dBm into the input of the module, and then recovering only minus 35 dBm means that, you know, there's a 35 dBm loss. It says by too small signal level, it could be the first or second local oscillator. Therefore, the output level of a YIG sampler should be checked at socket X22, and the level for the second local oscillator at socket X151 of the second IF converter. If the local oscillator levels are okay, the error lies in the converter. By checking the biases according to section 7.4.3.1, it is possible to determine whether the fault lies in the converter or the motherboard. Okay, so that's where we're at now. It talks about that X151. Well, if we have a look here, that's it there. So this module here, it provides a local oscillator output, an X151, and that goes into this socket. And then I think it talked about X22 as well. That's X134, not sure what that is. Let's have a look. That's X13 to X151. X134, what's that say? That's X13143, X132. Could it be this? Potentially. It says W17, but it goes off down to there. A140. Just trying to find X22. Because it did say that. It did say X151, which we found. X22. The YIG sampler should be checked at X22. So it might be on a different module. I'll have to find X22, X1, W, X138. Let's have a look there. That's X192. That's W12, X191, U12, W13. So that's X164. So I'm just trying to find X22. Not having much luck at the moment, but it'll be here somewhere. Anyway, we'll find that, but it's not at the top, because the top is just the RF input. That's all, just there, look. And there's no other plugs there, unless there's some on the top that I've not seen. It's possible. So we'll find that. So yeah, that's basically it really at the moment, until we get further into it and we'll see what levels we get. It does give some information there about what levels should be, which we're going to look at. Yeah, I think X22 is, we're looking at the top of the instrument now. We've turned it round. I think it's this here. I think it's an onboard connector down there somewhere. It's quite a bit in there. There's one or two RF, because this is the RF converter. So I think there's one or two other coaxial cables and things hidden down there as well, but there's definitely something there. Unfortunately, the jacket on this has turned round, so I can't see its reference, but I'm sure that's where X22 is. Anyway, we'll persevere. Okay, so according to the manual, it says connect to spectrum analyzer to X21, X22, remove this cable X139, I think it is, from the module. This model is an FSEB model, so it says basically set the span to 0, vary the center frequency between 0 and 3.5 gigahertz, measure the local oscillator level. Well, the FSEA level doesn't apply to us because this is an FSEB, so it's basically saying X22 we should be getting plus 12 dBm at the frequency range between 7.94 to 14.94 gigahertz, and the same X21 0 dBm, the frequency range 7.5 to 15.2 gigahertz. So we can check that on our microwave spectrum analyzer that we've got here. I did find out as well where the there's a YIG tuning, course tuning thing, but might look at that a bit later. But X22, because this is the module, and X21 were those connectors I pointed out on the board. It was actually this that I pointed to through the slot at the top, but I could see that there are others further down, as we saw in the previous section, so that's where they are, because this is where the YIG is in this area. And then the other modules that we need to connect to connecting at the bottom here. So that's what we'll do. We'll check those levels now and set the test up. Okay, so we've got the RF converter module now out of the test set. It's quite a big test set. It's very clumsy to try and deal with it because it's such a very heavy test set. Well, spectrum analyzer, and the modules are a bit of a sod to get out. There's like a rail, two rails underneath, which I'll show later, that slide to unlock all the modules so they can be withdrawn. But anyway, there's also screws at the side which clamp to this bracket, and in addition to that, I've taken a photograph of the RF cables that plug in on these sockets underneath so that I know how to connect them back. But this is the connection that we need to look at, X22 and X21, because this is where the YIG is. This is where the RF input from the RF attenuator comes in, which is obviously on this connector here via the RF attenuator, step attenuator. It connects in there. So we'll measure the local oscillator, but interestingly enough, while I've got it out at this stage, what I'm going to do is I'm going to undo all these screws and remove this just to see if there's anything obvious, any damage. The only reason why I'm doing that is because while we've got it out, we may as well have a look. And secondly, the person who brought this to me did say that there's a possibility that this instrument was fed with a large DC bias, high voltage bias up the RF input, or possibly a pulse of high level RF power. Now, it could be that there are some components in there which are obviously burned or broken that we might be able to see. So we'll have a look anyway, it'll be interesting. And then we'll connect an SMA test cable to one of these two ports and do some tests. Back with you in a moment. Okay, so I've got the can off now, and this is what we've got on the RF input. There's another can covering this. A bit reluctant to remove that at the moment to have a look, because obviously by removing that it could disturb its characteristics and its calibration. Don't particularly want to take that off just yet anyway, to have a look until we know this module's definitely faulty. But it's a typical Rhode Schwarz, where if you remember the CMS54 repair video that I did, where we had a very similar glass substrate type of PCB with etched onto it the semiconductors components, resistors. In this case we've got a bandpass filter coming in, as we can see these little planar tracers that we can see there, and they come along obviously before then going on to the next stage through here. And under these RF absorbers there are certain elements of the system that are under these. This looks like as if that's the YIG local oscillator mix coming in. This looks like the mixer, and so we've got the LO coming in on the right, the RF signal from what is this module from this bandpass filter connecting through, and that looks like as if it could be some kind of bias, DC bias there, perhaps, who knows at this stage. It's quite difficult to work out. It looks like as if that's potentially a DC feed there, may not be, but so it looks like as if the RF goes through from here to there, possibly. It's difficult to see without removing all these metal cans and things, but again, that could be an amplifier as well, and then it goes through to be mixed. Maybe the mixer's in this area here, possibly. It's very difficult to work out at this stage, but that's where we are. So as you can see, it's almost, well, it is impossible to repair really, because it could be that there's a defect anywhere along here where it's been overdriven with RF or a DC pulse, and it's popped what's under there, obviously damaged it. And these components, even if they were attainable like the CMS54, these substrates with the etched in semiconductors or resistors that we find on a lot of Rhode Schwarz gear, even if they are attainable, you're talking very, very high value. And as you can see in the CMS54 video, radio test set repair, that I looked at, the resistor, attenuator resistor for the RF input that was etched in on a glass substrate like this, the same type of component basically, material, it was £680 with a quotation that I got back from Rhode Schwarz just to have that little part of the module replaced, you know. So it, as it says though, there's no component parts available for this module, so naturally if anything on this module is faulty, then the whole module has to be returned back to Rhode Schwarz for repair. So what we'll do, we'll measure the oscillator feeds, the local oscillator, the first and second local oscillators. I think the second LO comes in down here, the first LO is fed in here. We'll see whether those levels are correct. If they are correct, then we can progress on to the next second converter module, but we'll just have a look and see where we are with the levels. I don't want to disturb things, particularly this can or whatever yet, until we know this module's fault. If we know this module's definitely defective, then I'll come back and take this can off and we'll have a look inside and see if there's anything obvious there. But I don't want to disturb things that are, you know, that can affect its performance permanently, because sometimes these devices, the way that the cans are put back on in a certain way, and they are tuned as part of that, and when you disturb it by taking the can off, or an RF absorber inside moves, or something that's been placed in a particular location, by removing the can it can disturb it permanently. So I don't want to do that just yet, and we'll check the levels and see where we are. Okay, we've reassembled the unit now, put the module back in. We've connected a little periscope sort of cable which goes to the local oscillator, well, the YIG output X22 connector from the RF module. So we've got that connected there, so we're able to connect that off now to the spectrum analyzer to measure the signal in accordance with the instructions to do that measurement. So we'll do that now. Right, so what we've done now is we've, as per the instructions, it says connect the signal output basically up to the spectrum analyzer for checking from X22, and also remove X139 as well. It says that, which is X139 is this little cable here that plugs in the middle of these two sockets. And then it says basically on the FSEB model, which is this test set is the FSEB model, we should be getting plus 12 dBm in the frequency range of 7.94 to 14.94 gigahertz, depending on what frequency you've set the spectrum analyzer to analyze. I've set it to 1.5 gigahertz. So without further ado, having a look at the screen here for the spectrum analyzer, we've got a frequency in the middle here of 9 point, I think that says 460 gigahertz, and the level is 12.75 dBm. So that level is correct coming out the YIG oscillator, so there's nothing wrong with that, and that's what it says on in the service manual as well. Yeah, quite clearly there for the FSEB X22 plus 12 dBm in that frequency range which we're getting. So that proves that that measurement is correct. So onwards and upwards. Right, so just in the process now reassembling it back to its original condition. We had the link disconnected which connects the YIG oscillator output to the LO input there, so we'll re-establish that. But how to make this up, well, I already had this actually from something else that I saved, but this allowed me then to insert the card back in its original position within the instrument without having to try and, you know, break out the extender card. I don't have one, you see. In order to fit inside the instrument, you have an extender card that then hires the module to this level, so it sits here, and then you can work on it. But in doing that, then you have to make all the other RF cables up as well that go at the bottom and extend those, which I can do, but I just don't have the extender card. So I had to make this sort of, because the gap is quite narrow when you insert this back in the instrument. There's only about, I'd say, a centimetre, half a centimetre between the face of this module and its adjacent module, which is just sat here, so the gap's not very wide. And unfortunately, what Rhode Schwarz have done, they have actually thought ahead though, but if you did have the extender card, it's quite easy, because then obviously they've cut these little grooves out so that then you can connect, you know, the cable in like that, you see, and connect up. I can't do that obviously in this context, because when you insert the card in these sliders, then the cable can't go through. But at least I've thought about that, which is sensible. But I've had to bend this solid rigid coax that I've got up slightly so that when the card's in, it just fits, and it's actually quite low profile. I think I've done pretty well there. But anyway, because originally I did start with all these fancy elbows and things, trying to get angles on the output so that I could bend the cable, but then of course the cable plugs themselves were too long and it protruded out too much. It stuck out like a sore thumb, so when you tried putting it in the instrument, it caught against the other module, so it wasn't worth bothering with that. So this is the way around it, you see, doing things like this. And with it being rigid coax, there's no loss, so you know, the measurement's more accurate than using some of these RG174, RG175 sort of ultra thin RF coaxial cables, which are not particularly good at particularly very high gigahertz frequencies, maybe up to 1 or 2 gigahertz, but RG174, 175 is quite lossy. You know, it's a similar diameter, but it's quite lossy at the higher frequencies. So I wanted to avoid, you know, any problems with that. So we'll re-establish that link back. We'll plug it back in. The next measurement, according to the service manual, is from there. Luckily it's one of these connectors down here, one of these two, where we then look at the local oscillator, the IF output, the IF level, which is X134. Remove that X1139 again, which is what we did in that other measurement, and it says span 0 and observer frequency at 30 megahertz plus or minus 20 megahertz, level minus 18 dBm, I think it is minus 18 dBm plus or minus 4 dBs. So we'll see if that level's there now, and see if the IF output's correct. If it isn't correct, obviously, then we know this module's failed, and that's where the fault be. Right, we'll get on with that now. Put it all back together. Just looking at the rear of the RF converter module, we've got, looking at the sort of architecture of it really, there's quite a few commonalities here that we have. I mean, quite a lot of these what appear to be voltage regulators, one for each part of the system. A couple here, and these are not sure what part numbers on them yet, but it looks to me like as if there's some kind of voltage regulator, if I can get the camera to focus on it. But I think this is where the supply rails are coming in and out of. So each part of the system within these cans, I believe, has got a voltage regulator for the different rails that it uses, and they crop up all over to these on this particular card. Likewise here again, 3 or 4 of them. There's quite a few here. Again they seem to be quite common on this module. So I've got a feeling, although I'm not 100% certain, because obviously there isn't a diagram for this module, but that might be worth a look at a bit later on if we do prove this module's failed, just to see whether those voltage regulators are giving an output. But it's obviously time consuming to try and do that. I don't think that that will be where the fault lay. I think it's an RF fault, but the interesting thing is there's none of them have popped. There's no obvious blistering discoloration, craters in them. There's nothing that's gone fizz bang or burned or anything. I can't see anything obvious on the board where, you know, we have any component failures. Tantalum caps that are scorched. Looks like as if that might be a 0 ohm resistor there. I think that blue one possibly, not sure. There's always the chance as well that if this RF module has failed because of an excessive RF input, be it DC bias or RF, that in the input, RF input, under that can that we looked at earlier, that there could potentially be a protection device, such as a resistor, 0 ohm through link resistor, surface mount, or something like that, that would pop in the event of you know, the RF being excessive. But then I wouldn't have expected, like we did in the earlier test, its frequency response to be, as far as level, to be uniform across its frequency range. It would sort of probably start off at very high attenuation at low frequencies, and as the frequency increased, then it would start to ramp up because of the transform effect of the RF being able to couple across the air gap at the higher frequencies more effectively than at lower. Well, we're not getting that effect here, so I don't think we're going to be as lucky as having a protective component on the input that blows open circuit when on the RF path when it's fed with excessive RF or DC bias. So the IF signal that we're going to measure comes from one of these sockets when I reassemble the module. I'll put that link back in now. Everything's nice and snug, tight fit, and we're ready to do that IF measurement now. Okay, so the instruction says connect to X134 on the RF converter module, which is the IF output, and measure a frequency and level, which we're going to do. These were SMB connectors, and this is the output then to the what is a second converter module from the IF. So I've found a SMB lead that I've had for some time, which has got an SMB plug on one end and then to an N-type N on the other. So we'll connect that now to the spectrum analyzer and do that measurement next. Okay, so this is X134 at the top, that connector there. It says in the instructions to remove X139, which is this that connects to that little MMCX connector down there. And then it basically says measure a signal then at a certain frequency. So we've connected that up then to the spectrum analyzer. We're getting something already, and according to the information it says for the IF level, it says connect spectrum analyzer to X134, which we've done, remove cable from X139, which we've done, and then it says setting on the FSE, it says span 0, vary center frequency between 0 Hz and 3.5 GHz, measure IF level at X134, frequency should be 30 MHz plus or minus 20 MHz, level is minus 18 dBm plus or minus 4 dBs. So if we turn the instrument round so we can see it, and so the watchers just set up the span center frequency. I'll put that at 1.5 GHz, the span 0 megahertz, so that's that, 0 Hertz span. Okay, span is 0, and then it says basically 30 megahertz. So frequency 30 megahertz, span is I'll put that just at 20 megahertz on my thing, just to see whether we can see anything. And we're not getting anything anyway. Let's have a look at the input attenuator level. Oh, we've got something there. Oh, hang on. We've got frequencies all over the place here. Connect spectrum, remove cable expert setting on the FSE. Vary center frequency between 0 Hz and 3.5 GHz. Measure the IF level at X134. Frequency 100 megahertz, 500 megahertz. Interesting. Marker, peak, and then what frequency is that then? 90.2 megahertz at minus 16 dBm. So the frequencies aren't correct for a start off. If I change the center frequency and move a center frequency, is it going to move? Strange. Doesn't mention anything about inputting a signal into the spectrum analyzer under test. Span 0. And then doesn't mention anything about that. That's strange. Frequency 30 MHz plus minus 20 MHz should be observed, which I'm not getting that. I'm getting a frequency elsewhere at 90.2 MHz at minus 16 dBm, but I'm not getting 30 MHz by any stretch of the imagination. So that seems a bit strange to me, but let me read on anyway, see what I can ascertain. Okay, well, according to the manual anyway, it says that we should be getting between any frequency between basically 0 and 3.5 gigahertz, we should be getting the 30 megahertz IF plus or minus 20 megahertz at minus 18 dBm. Now the strongest signal, if I open the span up to like 1 gigahertz. The strongest signal we're getting down is at 90 megahertz. The other signals are obviously weaker, but if I change the span back to say 10 megahertz and we go to a center frequency of 90 megahertz, I think it was, we're getting the frequency there. Now interestingly enough, if I change the center frequency on here to say 1 gigahertz, you can see it moves slightly. Obviously if I go center frequency again 100 megahertz, it moves again. Center frequency 10 megahertz, moves again. So it's meant to move plus or minus 20 megs, but the thing is the frequency is wrong. Instead of it saying it's 30 megahertz plus or minus 20 megahertz, because obviously as we change the frequency, center frequency of the spectrum analyzer, the IF will move plus or minus within, well, move within 20 megahertz. Now the level, if I go to markers and then go to where is it now? Just trying to find it. Let's see if I can see it on there. Right, marker, peak. Let's see if we can find, oh, peak, there we are. So it's minus 17 dBm. The level's right, but the frequency is wrong. It's at 89 megahertz, that particular frequency. Now if I go to 30 megahertz signal, let's have a look, change the span to say 30 megahertz width, I'm not getting anything at all in that frequency range. So it looks to me like as if that's where the fault is that unless there's a misprint in the service manual, you know, that it is a 90 megahertz instead of 30 megahertz plus or minus, but it definitely says 30 megahertz there, frequency 30 megahertz. Now it doesn't mention anything about inputting a signal to the front port of the spectrum analyzer in order to get that, but we might try that next anyway, just in case they've omitted that in the manual. But yeah, it's weird, very strange indeed. But if I go to span and set it up to 1 gigahertz, then we've got a multitude of frequencies. The peak though is at 90 megahertz, and then the next peak we can have a look at. Next peak right, for example. Well, we'll do next peak left. Oh no, that one at the bottom there must be, yeah, that's its own internally generated frequency. Next peak right. Let's have a look at these others. So that's at 178 megahertz. So it seems strange that I don't know if this is a misprint in the service manual. The only reason why I'm saying that is because it does measure a signal on the screen, albeit the level's wrong. Now, I would have thought if the frequency was totally incorrect, totally wrong, it wouldn't measure a signal at all. So I wonder if that's a misprint in the manual. I don't know. I'm questioning that now, because it clearly says 30 megahertz minus 18 dBm. And I've set the span to 0. I've connected the sockets as it shows there. So there's something not right there. I don't think there's something not right. But I'll have to look further and see what I can find. Anyway, I can't find anything in the manual that contradicts what's already written there. It says 30 megahertz throughout, but if I move that marker down to that lowest signal there, that's what, 2 megahertz, if that, 3 megs, and then there's nothing in the, it's around about there where we should be getting the signal, you see, around about 30 megahertz, but it appears there at 90 megahertz, and that does move with the frequency when you input the center frequency indifferently between 0 and 3.5 gigahertz, which we've seen. Then we've got a signal there. What's the frequency is that at then? 171 megahertz, albeit low. Another one, another tone there. It's about 258 megahertz. Next one, that's next biggest, is this one. I can get the damn thing to remain stable. It's roughly around about 393 megahertz, and then the biggest one, I suppose the second largest of them all, or third largest if you exclude the one on the far left, is 564 megahertz, and then minus 41, and then obviously minus 42 dBm, 737 megahertz. But one thing I can say is, although the frequency is wrong for this IF, it is actually the correct level. It does say minus 18 dBm, plus or minus 4 dB's error. Well, we're getting quite almost near that there, but minus 17. So I think the frequency conversion's wrong. It's obviously not converting it down to the correct frequency, and thus measuring the signal as it should do appropriately. So I think that's where the fault lay with the information I've just read in the manual, because we should be getting an IF at 30 megahertz and we're not. So naturally, with that being like that, then we're going to have problems in getting it to work. The RF level's going to be wrong, obviously. So I think that's where the issue is that it's not mixing the signal properly in the RF converter module. Probably the local oscillator, although the YIG's running fine with the sound of it. It could be the mixer itself, or it could also be that there's a secondary local oscillator within the module as well. There is a second IF input according to the information that I've got in the block diagram, which I'm just looking for now while I'm speaking to you. But it looks as if either the second local oscillator frequency is off, which is in that RF module, because as we saw earlier in the block diagram, there was a second local oscillator input into that module, but the first local oscillator is running okay, which is via the YIG. So I think the second local oscillator is off frequency somewhat, and thus it's giving an IF which is way out of the thing now. According to the information I'm looking at now, we've already been on to the local oscillator. There's a second one. Let's have a look. Yeah, on the RF converter module, we'd already looked at the first local oscillator, which comes from the YIG, which is fine. There's another one coming in though, X131, which is another local oscillator signal, the second local oscillator after the ×5 multiplier, and then bandpass filter, which is there. So it looks like if we go on to X131, that might be able to give us some indication. Because if that frequency is wrong, then the output where we're measuring at now is going to be wrong as well. So yeah, we'll have to look there now, I think. Okay, after doing a bit of extensive reading now in the manual and then coming back to the testing that we've just done, that test that we've been through is to verify that the YIG local oscillator is running, which is this section, and that's where we were on the output there at X134. Now that's another module that comes in after 2 or 3 stages on from the RF converter. This bit here, that's all basically all taken into account in that measurement before it then comes in again on this side here as an input, and then it gets mixed with the signal from the YIG to then produce the IF out here, the synthesizer. So basically that should be at 30 megahertz, it's not running at 90, which suggests that there's either a problem with the YIG oscillator itself running at the wrong frequency, i.e. it's failed, unless it can't tune, or the signal coming in here is also failed. But anyway, I've checked this signal and that's fine. So I think the issue's on this board then, obviously, in this part of the module, and that's under one of those gold cans that we were looking at earlier on. So I think we've sort of hit rock bottom now with this. I don't think we can pursue this fault any further, but we managed to trace it though right the way through. But the IF coming out here is way off frequency. Instead of being 30 megahertz plus or minus 20 megahertz, it's 90 megahertz, which is this probably remarking on this YIG oscillator not running at the right frequency. So there we are. It's just seems like one of those things. We've sort of hit the brick wall now. Obviously we won't be able to get spare parts or anything like that. It's definitely not a possibility. Not reasonable prices anyway, so I think I'll have to let the guy know who passed me the spectrum analyzer for looking at the bad news that looks like as if we're at the end of the road with it. Whatever's happened to it has obviously been quite serious, and that also may be the issue, that it's maybe been given a signal far higher than it should have been, or something else has happened to it that I don't know, and it has caused this fault. But I'm just going to have a reflection for a few minutes, just read up a bit more, and then come back with my final prognosis. Right, unfortunately it looks like as if further testing that I've just done has revealed that the YIG oscillator is running on frequency as per the earlier test, because that's where we looked at this output from the YIG here. The way the block diagram shows it is that it's all inbuilt in one module. It's on that one entire module, but it's consists of separate parts on that module. But we went on the connector earlier in the earlier test to check that the YIG oscillator was given a correct output from one of these sockets, which was correct. I've just done the test routine now for this X133, which is a sample in there into the comb generator, mixer, and then obviously then to provide the IF synthesizer output, which should be at 30 megahertz at minus 18 dBm, and it's not, it's at 90 megahertz. So I'm now 100% certain, according to the information, the test procedures I've followed in the manual, which you followed me on for most of them, though I have done some that are off camera. This module, which is on that second card there, one of the, as it explains in the earlier technical description, if you go back to that in the video, it will explain how that module works and its subcomponents. Basically this has got a fault on it, and the mixing that's occurring here is then producing a frequency which is not correct, so thus it's failing obviously to work correctly. Everything else is okay though from what we've measured, but it's just unfortunate that it seems to be in that module. It's one of these gold modules that's bolted to that large card that's in there, and as you've seen when we took the module apart earlier, just one section of that module, just have a look inside it. It's all specially engineered components and bespoke design and layout on these things. No hope of being able to repair that to component level, so I mean that's where we hit the rock bottom with this, I'm afraid. Such a shame really, but it's a beautiful spectrum analyzer. It's very nice, but unfortunately, you know, as nice as it is, it can't be repaired to component level, unfortunately, because of the repair methodology that Rhode Schwarz employ, which is modular replacement. It's such a sad thing really, but not to worry. At least we've tried anyway. That's the best thing, we've tried, and you never know, it may have been a fault which could have presented itself. By the way, just a quick one, the minus 12 volt rail, I did find the minus 12 volt rail. It does have its own independent ground connection on an isolated output. It comes from the power supply unit, and there's a contact down here which is the minus 12 volt ground reference point. It's isolated from chassis ground, which is the neg VE rail of the power supply for the plus 5 volt, 12 volt, 15 volt and 28 volt and minus 15 volt rails. So it's an independent thing, and it's for the microcomputer, what they call a transputer. So that was there, and it was never missing. It was just I was using the chassis ground as the measurement reference, and it isn't. It's got its own neg VE 0 volt connection for the minus 12 volt rail, so that wasn't an issue either. So right, we'll just collect our thoughts and come back now with possible ways forward. Perhaps have a look at some spare prices on eBay and places like that to see whether these modules are available on eBay, and look at sort of spare part situation to see whether that RF converter module is actually available. Okay, so we've reached the end of the video now, and I think it's really a lesson that with Rhode Schwarz gear, as nice as it looks and as wonderful as its spec, they are more difficult to repair than perhaps some other instruments. And I think anybody who owns a Rhode Schwarz instrument will ultimately at some point come across that issue. We've seen that the service manual makes clear reference to the modules not being repairable to component level repair. Now that's a great shame, is that, and if it had provided circuit diagrams for all the modules, then at least that would have helped us with being able to diagnose down to component level. But having said that though, as you could clearly see earlier on in the video, when we looked at the RF modules, the gold plated RF module that we took the lid off on the RF converter board, Rhode Schwarz and indeed other manufacturers as well employ, particularly spectrum analyzers higher spec as this one, bespoke designed componentry on either like a glass substrate, or it's a form of ceramic substrate where the components are etched onto that, and obviously that's to reduce the parasitic inductance and capacitances and all the undesirable effects that we get with RF at such high frequencies, particularly in the gigahertz range. And unfortunately what happens there is that it makes such repairs almost impossible. And as we've seen with other repairs we've done on Rhode Schwarz equipment, the component parts are extremely expensive. So this chap who's a radio amateur who owns this instrument, I'm afraid is going to be giving some bad news about where we've got to with the instrument. And if he wanted to pursue it himself afterwards by sending that module off that we've looked at to Rhode Schwarz, he could do that. I've been careful not to disturb anything that would invalidate any repair that could be done on the module, because obviously we've not removed some cans that were clearly put on as a calibration assembly when it was manufactured and obviously tested on a bench. So we've not disturbed anything as such, and I've been quite careful to make sure it's non-invasive, the repairs on what we've looked at so far. But clearly the frequency conversion aspect is wrong. Instead of being 30 megahertz, it's 90 megahertz. Now it could be a misprint in the service manual, but the service manual is definitely for this instrument, and it's not as if there's a different IF for different models either. It clearly says that that's not the case in the manual. Now there are some words in the service manual where they've translated from German to English which are incorrect spellings, and whether you could get a 3 and a 9 mixed up, I don't know, but it's possible. But the thing is that the information is mainly to modular level repair rather than component level, and unfortunately anybody who's in the repair business often finds that when we get such an instrument as Rhode Schwarz with a high price point, a high yield cost, in order to repair such an instrument, the repair costs are extremely high indeed. And we've seen past examples of that with the CMS54 radio test set repair video that I did. Now there are a lot of Rhode Schwarz fanboys out there, and there are a lot of Rhode Schwarz aficionados that swear by Rhode Schwarz, and that's fine, you know, I've no problem with that. I own Rhode Schwarz test gear myself. I have a selection of it, but as you can see, the theme with Rhode Schwarz repairs is one of a difficult task indeed, simply because the parts are unobtainable unless you go direct to Rhode Schwarz. They don't tend to deal with third-party intermediaries for supply of component parts or modules. It's mainly direct to Rhode Schwarz, so they have a monopoly over the instrument. Even long after you've purchased the instrument and you may then experience a fault condition, you still got that that onerous on having to return back to Rhode Schwarz, and that is obviously where the cost comes in. Now, obviously there aren't many spare parts floating around for this kind of an instrument, and I've just looked, and I've looked historically back on some websites that I know that sell component parts for various test instruments of all different manufacturers, all of whom don't show any indication that parts are available for this instrument, or have been so for many years. And of course, some of the parts that I do see on eBay and other sites that seem to suggest that modules are available for certain things, it's unknown, obviously, if that module's been tested or not, or whether it's guaranteed working. The modules themselves, even second-hand, can be very expensive, several £100 just for one module alone. So you're taking great risks in trying to repair such an instrument. If you're somebody like the gentleman that owns this, a radio am, and it's very difficult, to afford such spares, indeed to get any support. I've been very lucky, I think, with this instrument, that I've been able to find the service manual that I have for it on a CD-ROM, which I've downloaded onto my Apple computer, and we've been able to follow the service manual. But even so, the repair methodology is clearly modular level repair only, and not component level, and that is, unfortunate, I'm afraid, in this video, that we've not been able to repair the instrument. I would have dearly have liked to have done that and returned it in a full working condition to the chap who owns it, but at least it does work insofar as for indication purposes only. If you're not bothered about the RF level being accurate, a radio I may not be bothered with that really, but an indication of the signal presence, and also the fact that it functions in every other aspect apart from reading the incorrect level, then perhaps it's still usable even in that scenario. Now obviously I don't know what's happened to the instrument to cause the fault. My theory is that there's been an excessive level of RF power fed in on the input, the RF input, or potentially a high level DC bias fed in, and that's obviously caused the fault. Or it could just be a naturally occurring component failure due to age and obsolescence. Who knows? This is it. It's all a guessing game, but the frequency of that RF converter module is definitely wrong, and for that to happen, then obviously we can't then single out individual components on the circuit board then to try and find that fault, because we don't have any schematic information. And as you've seen with the construction methods of those substrates that are in those gold modules, you wouldn't be able to repair something like that even under a microscope. It would be enormously difficult to try and even attempt something like that and to have any success. And you wouldn't be able to get the components that go on that board anyway. If there were specialist microwave mimic devices or other kind of silicon pin diode switches, anything like that, the components are so small. They're basically bond wires, gold bond wires that connect from the semiconductor wafers to the PCB traces. So the chances of being able to repair such an instrument are extremely low, I would say, unless you're very lucky that the RF attenuator on the input has blown and you're able to strip it down and maybe repair some of the surface mount resistors that might be in it or whatever. But even then, you're clutching at the straws, you really are. Anyway, I hope you've enjoyed the video. I certainly have. I've enjoyed looking at the instrument. I've had the good opportunity to look at it with you. We've gone through all the servicing, the checks and the tests, analysing the calibrator, the RF attenuator, carrying out YIG oscillator measurements, power supply checks. We've done all the things that anybody else would do, really. So again, it's I think it's more about the journey rather than the destination, and the fact that we've gone through it methodically And we've not done it by guesswork either. We've used a service manual in accordance with the instructions within it, and we've been able then to analyse the test set further. And one thing as well before I do leave today is that the password for the service menu under the config screen, if you remember when we went into the settings screen under, I think it was configuration, when I can find it, info cal, and then we had mode setup, that was it. Under service, when you try and go into, say, the input RF, it then wants, say, a password or whatever in order to be able to get in it. You got to enter the password in here. Now the password is actually in the service manual, and anybody who gets the service manual will be able to look at the password info in there, enter that in, and then get into the service menu. Off camera, I've had a faff about with that, and it still doesn't work. So you can't win no matter what. You can go through all kinds of different avenues and processes and try and magic tricks, you know, but you won't get anywhere. Rhode Schwarz have seen to that, believe me. So the only way forward is to get the module out of the unit, put it in a bag and a box, and send it off to Rhode Schwarz, and then just hope your bank balance is sufficiently large enough to accept the repair costs, and obviously then get the module back, and then bingo, you're away. So with that, thank you for joining me today. I've enjoyed this, I hope you have, and obviously these repair videos are quite lengthy because of the fact that it's not Hollywood production. We don't cut loads of video out, and we don't show, we only show, you know, the best of repairs. Some repairs you win, some repairs you lose. It's the luck of the game, and it's just the way the cookie crumbles, and you have to accept that, you know, you can't always repair everything you get. So with that, thank you very much for joining me today, and stay tuned for other videos on test equipment repairs. Thank you, bye bye.